Hello everyone, my name is Long Qiu. I am a research scientist at KAUST. In this talk, I will present you our recent findings in exploiting temporal data reuse and asynchrony in the RTM. This is a joint work between KAUST and NVIDIA. By the end of the talk, you will learn how we integrate our temporal working approach called MWDTB into the RTM. The resulted implementation outperforms by up to 70% legacy RTM code on various shared memory systems using 6 short 3D datasets. Here's the outline of my talk. After a short introduction, I will give an overview of MWDTB stencil computation. I will then present how we designed MWDTB-based RTM. Some numerical results and performance will be shown as well. In the end, I will give a conclusion. In this work, we consider the second-order 3D acoustic wave equation with constant density. We select S-order finitely different spatial operator because it offers a higher accuracy and a reasonable computational cost. As shown on the right, such scheme requires 8 neighboring grid points to the central point along each Cartesian direction. Based on the above equation, the RTM algorithm reconstructs the source wave feed forward in time and the receiver wave feed backward in time. It then applies an image condition to extract reflectivity information out of the reconstructed wave feeds. Both forward and backward propagations in the RTM consist of thousands of time steps. The classic implementation of RTM would compute such wave propagation one time step after another. That is to say, for each time step, it accesses all grid points via 3 nested loops and performs computation. To enable parallelism on multi-core architectures, one may include OpenMP directives to parallelize these loops and take advantage of the cache. On such architectures, it is beneficial to implement cache blocking to work around memory bandwidth limitations and to increase performance. The spatial blocking is the most widely used technique in stencil computation for its simplicity and flexibility. Figures below illustrate that the reuse of spatial blocking applies to the stencil computation in 1D, 2D, and 3D cases. And for a big 3D domain, we can tie it to multiple 3D cube blocks and compute them with different threads using OpenMP. Figures here illustrate with 6 OpenMP threads. The workload of each thread is shown in different color. Temporal blocking approach is a performance optimization technique that aims to reduce the memory bandwidth requirement of stencil computations by increasing its cache reuses within successive time steps. MWDTB refers to multi-core wavefront diamond tiling temporal working technique. It is a new temporal working scheme for improving the performance of stencil computations on multi-core CPUs. For this, it uses different strategies in each dimension. For the innermost dimension X, it relies on compiler to do auto vectorization. For the Y dimension, it uses diamond tiling technique. For the outermost dimension Z, it uses wavefront parallelism. We will review both diamond tiling and wavefront parallelism techniques in the next few slides. Besides the reduction of the memory bandwidth pressure, MWDTB also allows overlapping computation and communication. Diamond tiling is a well-studied temporal blocking technique. The figure here illustrates the basic idea of its application in 1D grid. The horizontal axis Y is the 1D domain. The vertical axis is the time step axis. Each diamond tile has dependencies to the 2 tiles below as indicated by the arrows. All diamonds that have their dependencies 4 fields can be computed in parallel. In the simplest case, this will be all diamonds in the same row. The tile slope depends on the stencil radius, which is equal to 4 in our case. The height of the diamond indicates the number of the time steps that can be computed with the data usage. As the diamond tiling is used in the outer dimension in our case, we use 2-level nested OpenMP and the dynamic scheduling of the computation of different diamond tiles with different group of threads. This gives flexibility in terms of assigning parallel resources, since one can choose the size of the thread group and the number of group threads that compute simultaneously. Wavefront temporal blocking is another technique we use. As you see in the figure below, wavefront tiles are computed in an order from left to right. For correctness, the wavefront slope is chosen to be the stencil radius as well. By ensuring the wavefront tile fits into the cache memory, the update order in this technique maximizes the reuse of the most recently visited grid cells. One must notice that if we want to enlarge the number of time steps inside a wavefront tile, we have to enlarge the corresponding size in diamond tiling, thus would also enlarge the cache size requirement of the wavefront step. Both sides of the diamond tie in space and time are tuned automatically in order to ensure this constraint. Here is a figure that illustrates a 3D view of different waveform steps combined with the diamond tiling technique. Each waveform diamond tiling step is computed using multi-threads running on multi-cores sharing a cache level. As a result, the memory bandwidth pressure can be reduced. Figures here show a 3D view of one waveform step where each thread updates and are denoted by a different color. As you can see, each thread is assigned to one or multiple consecutive time steps of one or multiple positions in Z direction. Threads compute distribution is mainly in Z direction, and up to 2 threads in the Y direction can be used as well, since it is symmetric. By ensuring the length of the waveform step to be a multiple of the number of threads sharing the work in the waveform direction, we can thus generate a well-balanced workload among all these threads. The length of the waveform step is another auto-tuning parameter, so that we can generate the most performing configuration for a dedicated hardware. The memory requirement of running MWDDB-based stencil computation is the same as that from spatial blocking approach. Only 2 arrays for setting 2 previous time step t and t-1 are required. After the computation, the array which holds the time step t-1 will be updated to the time step t+1. We alternate the use of these 2 arrays as input and output to compute all the time steps of stencils within diamond. Once the diamond is processed, these 2 arrays only save the latest 2 time steps of each stencil following the shape of the diamond. For our interest in the forward propagation, we save only the red part here, which represents the latest time step of each stencil in the diamond. So we let the MWDB keep benefit the shell cache as always. Once diamond is fully computed, we save. As you can see, the time step we saved in the forward propagation are no longer to be the same across the Y direction. That is actually a zigzag pattern. Same applies to the backward propagation. The reload of the forward wave feed and the corresponding image condition computation and accumulation appear only in the beginning of the scheduled diamond. In this way, the I/O operation remains asynchronous, but it still have a good size to maintain the efficiency of the operation. In terms of the source and the receiver injections, we highlight that due to the seismic survey, they only appear on a limited number of Z, so we can sort them using their coordinates according to the diamond shape. Therefore, their impact on the performance is limited. Here is a picture of a summary of the time integration of the RTM in the context of MWDDB using only one-dimensional space and time for simplicity purpose. During the forward time integration, the initial condition is represented in gray with 2 lines due to the second order in time of our equation. For the backward time integration, the initial condition is now the latest time step from the forward time integration. It continues backward in time until its completion. As diamond computations can dynamically progress in time asynchronously, a snapshot of a whole domain is impossible. That's the reason why we introduced the intertwined snapshot interfaces and imaging condition by consolidating them with the MWDB stencil kernels. The general theoretical rules to maintain the accuracy of the final image is that the snapshotting and the image condition need to be happened at the same time steps. For that, we add 1 extra time step in the beginning of the backward propagation using spatial blocking. We complete our implementation by adding a simple absorbing boundary condition with 20 lattice points in each direction. Figures below show a modeling of an impulse over time. The wave reaches the domain boundary and gets smoothly absorbed by the ABC with relatively small reflection. We evaluate the MWDB-based RTM with boundary condition and compare with the classical SB results. On a simple 2-layer model, the placement of the reflector using MWDB matches perfectly with that using SB. On a short 3D model, where a salt dome appears in the middle of the model, with the 100 migrated shot, top and bottom of the salt is a well image with MWDB. No shift in space is noticed between SB and MWDB in the migrated image. For performance evaluation, we use a various generation of Intel processor, including Haswell, Skylake, and Cascade, and AMD EPIC Rome. The configuration of each system, build environment, and the running settings are shown in this slide. These curves represent the performance of a node in terms of the gigastencil per second. For multi-thread performance on a node, MWDTB beats SD in terms of the scalability and the performance for pure snapshot performance on all these architectures. For modeling performances, the trend remains identical, where the performance is slightly lower. For measuring the MWTB-based RTM performance, we use 3 different grid sizes. The width of the ABCs is set to 20 grid points in each direction. The performance trends on each system slightly decreases, and we move from small to larger grid size due to the exhaustion of cache resources. The highest performance of RTM is achieved on the AMD EPROM system using in-memory snapshotting. We limited the number of time steps accordingly to ensure we have enough space in memory on each system to store the snapshots. The asynchronous in-memory snapshotting RTM based on MWTB reaches up to 70% performance improvement over its SD counterpart. Although the memory is inexpensive resources, this in-memory snapshotting experiment is of interest when combining with an I/O buffering framework. For out-of-core snapshotting, the MWTB-based RTM reaches up to 40% performance improvement over its SP counterpart. Here, we represent the performance impact of varying the out-of-core snapshotting frequency on SP and MWTB-based RTM using Cascade Lake. We show both performance of forward and backward propagation using different domain size. While the SP performance remains identical between forward and backward, the MWTB's forward performance is significantly less than its backward performance. The F-write operation may become a performance bottleneck for MWTB RTM when snapshotting too frequently. We hope this can be further improved with I/O buffering framework. MWTB GPU porting is an ongoing work. Let's first review some of new features in the memory hierarchy of 800. Except the much faster global memory bandwidth, the combined capability of L1 data cache and shared memory in each SM is improved so as the L2 cache size. This means that the larger portion of data sets can now be cached and repeatedly accessed at a much higher speed than reading from and writing to global memory. Besides of these increased hardware capabilities, 800 also increased asynchronous copy, allows asynchronous copy and barrier, which enable better use of memory bandwidth, and L2 residency controls that allows developers to set a portion of the L2 cache and manage data to keep and evict from that cache. Our current MWTB needs some adaptation in order to benefit to the new hardware. The current CPU design using vectorization offers by the compiler is innermost dimension. As shared memory is a treasure resource, such design will not be a good option for GPU. Classical 3D SB implementations uses 2D tiling and streaming in the last dimension. As MWTB is the 3D spatial dimensions plus 1D in time, we must leave at least 1D either from spatial or from time for streaming in order to reduce the pressure on the shared memory. We will also improve the data locality of the wavefront computation so that different bandwidths can still be computed simultaneously with the benefits from the L2 cache reuses. Here's the summary of my talk. We describe how we integrate the asynchronous MWTB approach into the RTM. The resulting implementation outperforms by up to 70% the legacy spatial blocking-based RTM on various shared memory systems using 6 short 3D datasets. To our knowledge, this was the first time the applicability of asynchronous executions throughout the whole RTM phases. For future work, we will consider offloading the I/O snapshotting operations to the I/O buffering framework like a multi-layer buffering system, MLBS. By adding support to MLBS, our MWTB RTM may overlap the write and read I/O operations with stencil computations while buffering the domain solution in the main memory. Moreover, we will also port the MWTB RTM on GPU hardware accelerators. We will also take advantage of the new Magnum I/O feature, which permits to bypass the CPU and to directly write onto the fast storage media. That's the end. Thanks for your attention. I'm ready for getting your question.